Let me, oh shoot, that's not what I meant to do. We're gonna go ahead, well, you know what, we don't have any Pear Deck slides. It's fine, we're just gonna keep going like this. I was gonna try to put it into a Pear Deck, but I think we're just gonna do it in the chat instead of doing a Pear Deck. Okay, so like I said, we were ending on this slide, right? Miss Hirsch added a couple of things. Sauce group session starts here. Momentum practice. We did this one where we had the car 1,500 kilograms with a momentum of 50 kilograms, and we found the speed of the car. Great. So then we have a couple of things to talk about. So just as a warm-up, what is momentum and what is the equation for calculating momentum? So let's go ahead and bridge a little bit of what we learned from yesterday and go ahead and get our minds into that right headspace. So what is momentum? Let's start with that one. So go ahead and either answer it verbally or in the chat.
The speed and like energy you get. I don't know how to explain it, but
yeah, you're getting there. Keep going. You got it.
And then the equation is P equals mv.
Yes, you got it. So the equation, P is for momentum, M for mass, V for velocity, right? So you were on the right track, Madeline. So it is. So when we talk about momentum, we're really talking about the movement of an object. When you've got something moving and that is moving and generating that energy, we say that it has momentum. And so when we think about momentum in the equation, we realize that there are two variables, two factors that go into this idea of momentum, and that's the mass of the object and the velocity. Now, when we think about momentum, it's really, it really has to do with like inertia and momentum go hand in hand. We haven't really talked about inertia, so I'm not going to go too far into it. But momentum is once you've got that ball rolling, once you've got that mass of the object and it's moving, it's got momentum. So that's kind of why we say like, all right, when you've got momentum, keep going with it. You're moving, you're going towards something, right? So that's the same idea when we're talking about it in physics. You're moving, an object that has mass is moving. That means it has momentum. And we think about the mass of the object and the velocity at which it's traveling at, and that's going to be the momentum of an object. So we're going to talk about how momentum comes into collision in a second. We already saw the conservation of momentum when we watched the video yesterday. So similar to the conservation of energy, right, which we've been drilling this in for years now, the conservation of energy is that you can't create energy nor can you destroy it. It can just be transferred, right? So energy already exists. It's just how we harness it. Well, that's the same idea with momentum. There is this thing called the conservation of momentum. And that means that the momentum before the collision is equal to the same amount of momentum after the collision. It just depends on what objects are moving before and after, right? So for example, if we go to this picture, in this picture, we talk about how all of the momentum is in the soccer ball. And that's because the soccer ball is the only object moving. The face is not moving yet. So all the momentum, so technically his velocity is 0. And what's anything times 0? 0. So all of the momentum is going to be in the soccer ball that's moving before the collision. But once you actually hit another object, you can start to see that there is movement in his face. So now there is a velocity to its mass. So, but there isn't as much movement going on in the soccer ball, although there is some movement left. So then we start to recognize that the amount of momentum before the collision is equal to the same amount of momentum after the collision. It's just that the objects are sharing that momentum. Does that make sense?
Is that why his head got pushed?
Yes. Mm-hmm.
Okay.
Exactly. Yeah. Good. Okay, so we're going to talk about force and momentum in a little bit here. So we really have to take into consideration force and technically what we call impact, which we're going to get to today. So let's go ahead and talk about this. We already went through this. If a large truck and a small car collide head on, which vehicle will experience a larger change of momentum during the collision and why? So I kind of talked about this already. So let's have you try in your own words to explain where there would be a larger change of momentum during the collision. Would it be in the small car, the large truck, or would it be the same?
The small truck
Okay.
or the large one? I don't know.
Well, yeah.
Well, the momentum from the large truck would be transferred over to the little car, and the little car would be like forced backward or to the side because it's smaller, has less mass.
Good. Okay, so we're getting to a good point. So you're thinking a little bit more about the mechanics. I want to bring your attention to this though. Remember we just talked about this? How all of the momentum is in the soccer ball, but then after the collision, the soccer ball shares the momentum with the face. So technically, the momentum is the same on both sides of the equation, before the collision and after collision. So thinking about that same rule of thumb, what is the situation going to be for this? Is there going to be a change of momentum?
I mean, is it going to change like from like it's giving it to someone else? That's like the change.
Okay, good. Yes. So Madeline, you're getting a little closer. So yes, we're going to be sharing the momentum, right? So before you've got a truck and a small car moving towards each other. One has a higher mass, one has the other mass, but the entire system is still combined. And then it hits each other. You're going to see that there is a bigger change of velocity and distance, but the momentum altogether is actually the same, right? So we've got the change in momentum in the truck is actually equal to the change in momentum in the car, but like Abby said, it's going to be going in the opposite direction because the truck is the one that has more mass. But remember, it's all the same system. So it's just a transfer of momentum. It's the same amount, but now one has a little bit more momentum and the other one has a little bit less momentum. That makes sense? Okay. All right. So then this is where we kind of broke down that equation, right? So this is what we ended with yesterday, where we've got the change of momentum in the truck is equal to the change in momentum of the car, but that negative in physics is telling us a direction. We don't have negative values in physics. We just have opposite direction that it's traveling in. And it's all relative, right? So then we break it down. So that P is equal to mv. So now we're talking about the change in the mass of the truck times the velocity of the truck. And that is equal to the change of the momentum, which is the mass of the car times the velocity of the car. And if we were to break that down even further, so first of all, are you guys comfortable with this equation right here? You guys see how it goes from the change of momentum and then they break it down into that equation and they replace the P with the equation?
Like, okay, well, what's with like the
triangle?
So, like, the triangle, what was that again?
It means change of.
Okay.
Yeah. Does that make sense?
Kinda. Can you explain that again?
Sure. So remember that we have an equation P equals mv. I'm going to put it in the chat for us. So we've got P equals mv, right? So basically, you could change these out. They're equal to each other. Mass times velocity is equal to momentum, and then you find the momentum by doing mass times velocity. So we can take that mv. So we know that the change in momentum is the equal but opposite direction to the change of the car, right? Momentum of the car. So then we can take this p and replace it with the equation. Now, these subscripts is telling us that mass and velocity is specific to the truck, right? And that change is just going to be applied to the equation. Same thing over here. That's why we break it down to the mass and the velocity of the car, because those are the two factors that determines the momentum. Does that make sense? Yeah? So then, to take it one step further, we need to think of the context. Before and after the collision, the mass of the truck doesn't change, nor does the mass of the car. It's not like as soon as they hit, chunks of that piece of truck is now becoming part of the car and causing there to be a change in mass. Those two are actually the same. It's the change in velocity that is shared between the two cars. So like if you think about the truck is going a little faster because it has a greater mass, it's going to maybe have a higher velocity. And then when it hits the smaller car, it's going to change the velocity of that smaller car because it's got probably more momentum. Does that make sense? So the big thing that we're talking about here is the conservation of momentum. Knowing that the total momentum from before the crash is going to be the same amount after the crash, it just may share that momentum, may transfer that momentum. Good? Okay. So let's go into this next problem. So this was taken directly from the book. And so you do want to have that book handy because we are going to be using a lot of example problems from that. So we've got a situation. We've got an example of conservation of momentum and collisions. And if you have the book handy, you can go ahead and open it to page 117 because this is right in there. So we've got two football players collide with each other. One player has a mass of 85.2 kilograms and is traveling to the right with a velocity of 1.43 meters per second. And the other player has a mass of 78.6 kilograms and is traveling to the left with a velocity of 2.19 meters per second. What is the total momentum of the system before and after the collision? So do you guys have your books open to page 117?
Yeah. So for this question, are we like multiplying the two?
Yeah. Mm-hmm.
Okay.
I'm going to open it up for me as well. Okay. So there's two things that we're going to want to identify, right? We are going to want to identify what the momentum is for each individual player. That's going to be the first step that we're going to do. So I'm going to open up a whiteboard. Although I think I probably could figure out how my Ladybug works, but next time I'll have to do that. Let's hope that this doesn't get all weird again. Okay, so we've got player one. So I want to figure out how I'm going to do this. So player one. Can you guys tell me what was player one's mass and what was his velocity?
The mass was 85.2 kilograms.
Good.
Yeah, and the velocity is 1.43 meters per second.
Great. And the velocity was 1.43, you said, meters per second. Awesome. Now, they say that player one is going to the right. So one way that we are going to be playing and showing direction is by adding that positive, right? So this is going to be positive because it's going to the right. So we are choosing that to the right is going to be the positive direction. Does that make sense? Okay.
What
So
do you mean by to the right? Like, what does that mean?
like if you were looking at a football field, you would see one player moving to the right. So like
Okay.
to your right. No problem. Good. So that we're going to put the right to the positive direction, right? So now we want to solve for the momentum of player one. So if we know that momentum is equal to mass times velocity, so what would our equation be? What's the equation going to be?
The equation is going to be P equals mass, which is 85.2 over velocity, which is 1.43.
Good. So be careful though, because you said over, which means that that would be division, but we want to multiply these numbers.
Oh, why did I do that?
I think it's because last time we were moving around the equation, so that might have been a little bit of a confusion, which is totally fine. So then remember that this is going in the right direction, like to the right. So it's going to be positive. So what is the momentum of player one?
121.836.
Good. So we're just going to round that to 122. And don't forget the units, which is kilograms times meters per second. So this is the momentum for player one. Great. Now let's find out the momentum for player two. What was the mass for player two?
The mass was 78.6.
Good. And what was the velocity for player two?
The velocity was 2.19.
Okay, but pay attention, it was 2.19, but now what direction is this guy going in?
Oh, negative 2.19.
Good, right? Because velocity is the speed with the direction. So if we know that one player is moving to the right and we've identified that moving to the right is positive, then a player moving to the left would be negative. It's just going in the opposite direction. So they're really going like this. They're going towards each other. So we want to know what the total momentum of the system is before and after. We need to finish figuring out what the momentum is for player two. So we know that P is equal to mv, P being momentum, m being mass, velocity is v. So what is our equation for player two?
78.6 times 2.19.
Good. But don't forget, we need to include the direction. So it is going to be multiplied by 219, but don't forget that we need to include the negative, right? And then remember that that negative is just telling us that they're moving in the opposite direction of the other player. So then what does the momentum for player two come out to be?
172.134.
Good. And then don't forget, we need to include that sign. So remember, we're doing a positive number, multiplying it by a negative number. So what is the sign going to be for this number?
Negative?
Yep. And our units, kilograms times meters per second. Good. So now we've got our momentum for player two. All right. So we've got our momentum for our two guys. So far, so good? Okay. Now, I want to do one thing. I am a visual learner. So for me, it really helps when I have a picture drawn, right? So player one had a higher mass but was going at a slower speed. And was his mass higher or excuse me, let me start with this. Whose momentum was greater?
The first one?
The momentum. Which momentum was higher? I know that the negatives make it seem like it would be different, but remember that is the direction. So it's not an actual numerical value of negative 172. It's just telling us it's 172 to the left. So which player has the bigger momentum?
The second one.
Yep, this guy, right? So I'm going to show that this guy, so player two, right? That's the same color. Yeah. So player two is going to be coming from the left. This is my football player. Okay. I know. Really well done. And so
It's actually not that bad.
really, I can't believe it. That's really funny. So remember, I like to do visuals. So for me, seeing a visualization of it is really helpful. And so if we know that player two is going to have a bigger momentum, I'm going to draw my arrow and my person with a higher momentum, bigger than my person two. So then I've got, I'm going to draw this guy smaller because he's got smaller momentum. He is going to the right, okay? And then we could even put our values in. So we know we need to know what the change in momentum is going to be, right? So this is the system, you guys. This is the entire system. So what was the momentum for player one?
The momentum was 122 kilograms.
122.
Times.
And, oh wait, no, this was player one, right? Yeah. Okay. And what was the momentum for player two?
$172.
172. Now we want to know the total momentum of this system. So if we want to know the total momentum, what we have to do then, this is the system. This is what's happening. This is the two things that are going on before the collision and then after the collision, right? So if we want to know what the total momentum is of this system, then when we want to know the total of something, what math function are we doing? If we find the total, are we multiplying, subtracting, dividing, or adding? When we find the total of something?
Adding.
We are adding. So now what we want to do is add this together. We want to find the momentum of this entire situation. Okay? So now what we're going to do is we're going to open up another whiteboard. So we know that we've got the momentum of player one is equal to 122. The momentum of player two is 172. Now we already did the math for the mass and velocity. So we don't need to do it again. We found that momentum. But if we want to find the total momentum of the system, and we just said that we need to add these two together, and I need to make sure I include my negative here, then what are we adding together in this equation? So the momentum of the system, what are we going to be adding together?
Both momentums.
Correct. And so that's going to look like what?
122 plus 172.
Okay, but close. Remember that this negative we need to include that negative, right? That negative is going to come with the 172 every time.
Oh.
So it is going to be 172, 122, and 172. So we can say we're going to add plus the 172. That's fine, but remember that we need to include that negative. So really what's happening here is we are doing 122 minus 172, right? Because if we add a negative, then it just means really subtracting it. Yeah?
Okay.
What is our answer going to be for this?
Negative 50?
Negative 50. And that, my friends, is the momentum. That is the momentum before and after the collision. Now, remember, this negative represents the direction it's going to go in, right? So if we have player 1 and player 2 colliding, which direction are they going to move in? Is player, right? And I also have it in an image here. We've got a bigger guy with more momentum, and it's going to collide with a smaller velocity. Technically, the masses are bigger, but whatever, the momentum. The momentum, and so the momentum of this guy is meeting with the momentum of that guy. Which direction, when they collide, which way are they going to go? To the right or to the left?
To the left.
Right. And so we represent that with our answer over here. So overall, the momentum of the system before and after the collision is going to be negative 50 kilograms per meter per second. That makes sense?
Yeah, I think so.
Yeah. Good. So remember that the momentum is going to be the same before and after. It's just the objects that are going to change that momentum. Okay. All right. Any questions before we move into the next one? Great. Okay, we're going to go on to the next problem. There are several of these. I want to make sure that we go through the lab though. So we are we're 27 minutes in. So why don't at 45, wherever we are in 15 minutes, wherever we are with the math calculations, we'll just skip to the end, okay? To the end of the lesson so we can get that lab report in. Okay, so again, so this was kind of exactly what I was drawing on the whiteboard, right? So we calculated the momentum for player 1, the momentum of player 2. Please do keep in mind that those negatives play a huge part because they're talking about the direction. So that is why it's important to carry that negative with the 172, because if you didn't, then you would have added these together and it would have just been 294, and that would not have been the correct answer, right? So making sure that we're bringing that negative, meaning the different direction. So this was exactly what I was doing. I drew a bigger arrow, bigger guy for player 2, more momentum, less for player 1, and then we added it together, where we got our negative 50 kilograms times meters per second. Okay, so according to the law of conservation of momentum, the momentum is the same after the collision. So the initial momentum is same as the after momentum. So they experience 50 kilograms times meters per second of momentum to the Okay, so now we're going to talk about elastic collision, which is also on page 118 of our book. So when we talk about elastic versus inelastic collisions, elastic collisions is usually when it's just two objects, they come together, there's a little bit of give. When we talk about elastic collisions, however, there's a little bit more that after the objects collide, they move a little bit more independently from each other. So they kind of like bounce off of each other versus like bounce in and move together. So we've got a wagon with wagon 1 that has the mass of 0.8 kilograms that's moving with a velocity of 0.2 meters per second to the east. Which way is to the east, right or left? If you think that this is north, south, which way is to the east? Is it to the right or the left of us?
The right.
Mm-hmm. Good. Good. So, my dogs. Okay. And so we've got our wagon 1, we've got the mass, we've got the velocity. Now, it collides with a stationary second wagon that has a mass of 0.5 kilograms. If wagon 2 has the momentum of 0.13 kilograms times meters to second east after the collision, what is the final momentum of wagon 1? So there's a couple things that we have to do here. Again, we want to identify the momentum of before the collision, right? So we're going to want to, let's go back to our whiteboards. We're going to want to identify the collision, initial collision. So our initial momentum, which just means that it is before the collision. And so what is our system, right? We've got a wagon 1. We've got our wagon 2.
Are you meaning to draw over the stuff we did last problem?
No, is that what's happening?
Yeah.
Darn.
Not for me. I can see normally.
Oh, for me it was.
That's just you,
Sorry.
Abby.
Oh, Madeline. Is it better now, Abby?
Oh, yeah.
Okay, cool. Cool. I just like restarted it. So much sass. I love it though. Okay. So then we've got wagon 2. Okay. So we have our system. So we need to know what the momentum is of our system. So how are we going to find our initial momentum? Think about what we just did. What did we just do between these two? We want to know the total momentum. When we do total momentum, what are we
You
doing?
have to add it.
We're adding it. So what we're doing is we are adding the momentum of wagon 1 to the momentum of wagon 2. Now, this is where we need to kind of take into consideration a couple of the information that we were given. So do you guys have the problem open up on your page? Okay, so then what is the mass? What did they say the mass was for wagon 1?
It's 0.80
Good.
kilograms.
And what was the velocity of wagon 1?
Didn't mean me. No. 0.20.
And direction?
Oh. It's to the right.
Good. So we're going to say to the right or to the east, and that's going to give it a positive, right?
Yeah.
Okay. So now, what was the mass for wagon 2?
It doesn't say. It just says momentum.
Check that second sentence where it says it collides with this stationary second.
It's 0.50 kilograms.
Good. And then Madeline, I want you to follow up with that, what I just said in a second. So what if the mass is 0.5 kilograms? What is the velocity of the station of wagon 2?
It doesn't say.
Right, because it says it collides with a stationary second wagon. When something is stationary, what does that mean? Is it moving?
No, it's not moving.
It's not moving. So if it's not moving, what's the velocity going to be?
0.
0. Good. So in our first example, okay, so if we go back into here, so let's go ahead and find out what the momentum is. What is the momentum of wagon 1? Remember that we have to multiply these. So what is the momentum of wagon 1 going to be?
Point 16.
0.16. Good. So we've got 0.16 kilograms times meters per second, right? And what is the momentum for wagon 2?
I think the book
13.
says it's, yeah, the book said it was 0.13.
Okay. I'm doing it a little differently than the book. I'm breaking it into different steps. So that's probably why, I mean, you are not wrong, my dear, but we're going to just break it down into a little differently. Okay. So, well, now you got me all nervous. Hold on.
What happened?
No, Abby was just looking at the whole problem, which is great. I'm just doing it a little differently than the book is doing it. So I think it's just a little confusing. So, but then she got me all thrown off because I was doing I was breaking it down into chunks.
Okay.
So I just want to. Yeah. Okay. I got it. I got this. I got this. Okay. So then what is the momentum of wagon 2? If we're just looking at this thing first, let's look at this before we get to the book. So if we've got the mass is 0.5 kilograms and the velocity is 0, what is the momentum of wagon 2?
0 because it's not moving.
Exactly. So we've got, and this is very similar, you guys, to what we saw when we were doing the soccer ball head, right? So we've got 0 kilograms times meters per second. So let's go back up to our initial momentum problem. Very quickly, hold on. So we are going to put it into the place of our equation, right? So we've got 0.16 plus 0. So where is all of the momentum happening before the collision?
The first
Wagon?
wagon? Yeah.
Right, exactly. And so we have this initial momentum of 0.16 meters per second. And this is also going to be the same as the final momentum. Remember that there needs to be the same amount of momentum before and after the collision, the conservation of momentum. So now we also know the amount of momentum for after the collision, right? So this is kind of where it comes into, we need to know a little bit more about our after, because remember the question is asking if wagon 2 has a momentum of 0.13 kilograms times meters per second east after the collision, what is the final momentum of wagon 1? So then when we're going to move into the second part. Does this make sense now? So far, does this make sense? We just figured out the momentum before the initial reaction.
Yeah, but didn't we already have that?
Yes, I was just setting it up so we could had the mass and the velocity of one. We have the mass and velocity of the one wagon and now the second wagon. So we just figured out the initial momentum. So now we need to use this initial momentum to do the second part of the problem, which was finding the final momentum of wagon one, because we don't know what that is, right? Remember that momentum before the collision, it was all in wagon one. It collided with wagon two. And even though the total amount of momentum is going to be the same from the before the collision to after the collision, that doesn't mean that it's going to share, it's going to transfer some of that momentum into wagon two. So now we're trying to figure out, after they've collided, what is that momentum for wagon one? Does that make sense?
Yeah, so we're just gonna add the two carts.
Which we already did. Yeah, so we did 6.16 plus 0 is going to give us the initial of negative of 0.16.
Okay.
Okay. So now we're going to move into that second. So after the collision, so we had our wagon one, we had our wagon two, we've got our wagon one. It hit wagon two, it collided. Not my best work, right? They came into each other, and so now, oh, that was too big. So now we want to find, so remember that initial velocity was 0.16, right? So remember that the initial velocity is also going to be the same as the final velocity, which is also 0.16. But we know that wagon two has a momentum of 0.13 kilograms. So this book is confusing me. I know what I'm doing. Okay. So we've got this final initial of, so the after the fact, right? Now we know it's how the book is telling us that we've got wagon two has a momentum of 0.13 kilograms after the collision. So all of a sudden, this wagon is going to have traveled farther. Remember, it's going to pick up some of that momentum. And now it has a final momentum for wagon two is going to be 0.13 kilograms. So if the total is, if we're trying to find out, remember that our final momentum is wagon one plus wagon two. And if we know that the final momentum is going to be 0.16 because that it has to be the same, it has to be conserved. We don't know what wagon one is yet because that's what we're trying to solve for. But we know that it has to be added to wagon two, which was 0.13. So then what is our wagon one final momentum going to be? Yeah.
0.03.
Yep. You got it. That is the correct answer. So did that make sense? Do you guys have any questions on that?
That makes sense, I think.
I think
Yeah.
I did something wrong.
What are you looking at? Yes, tell me.
I thought wagon one's momentum was 0.
Wagon one's was not 0. That was wagon two.
Huh? For
So-
momentum, what?
So remember we just did the initial, right? So we had to do the initial to find out what the total momentum was. And in our lesson yesterday, we said even if something is not moving, we should still include that in our total system. So we know that wagon 2 had a mass of where did it go? 0.5. I don't know why that went away. It has a mass of 0.5 kilograms. However, it wasn't moving. It was stationary. So when we do the momentum equation, it's mass times velocity. If we do the mass times the velocity and the velocity is 0, then all of it is 0. So there is no momentum for the wagon because it's not moving. But we do have wagon 1 that is moving. It's moving in the positive direction to the east, which is 0.16, because we do the mass times the velocity, which was 0.8 times 0.2, and that gets us the 0.16 kilograms times meters per second. That's the momentum for wagon 1.
Then where does 0.13 come in?
Because the problem told us. So if we look at the problem, it says if wagon 2 has the momentum of 0.13. So it was telling us already that after they collide, that momentum changed and caused wagon 2 to move. And that they told us in the problem that they had a momentum of 0.13. So we were solving for the leftover momentum in wagon 1.
Oh, okay. So like after the wagon was hit, it has
Yes.
a moment. Okay, that makes more sense. Because like
Yes. Good
wagon
question.
2.
Yeah,
Oh,
no,
yeah.
you got it. That was awesome. Good. And so we had a challenge, but like I promised, it is exactly 46 minutes. So I'm going to move into the lab. Unless you guys want to take a couple of minutes to do this. Do you want to do the challenge or you want to come back to this if we have time?
Come back to it.
Okay. No, it's good because we're going to get to the lesson. So we've got lessons 1.5, 1.6, and 1.7 coming up. And this is the lab. So Peyton was talking about this a little bit and asking questions about this yesterday. So I just want to go over it a little bit more in detail. So 1.5 is the lab number 1. 1.6 is the discussion, and 1.7 is really just saying if you didn't finish lab 1.5, lab 1.5, go back and do it now. So 1.7 doesn't really have its own activity. It's just giving you extra time. Does that make sense? Okay. So a couple of things we need to talk about in order for us to understand exactly what we're trying to get to at the lab. We know that momentum is equal to mass times velocity. We know that there is momentum that is conserved in the situation. Whatever the momentum is before is going to be the same momentum after. Now, we've been talking a lot about collisions. We were talking about when cars hit each other, and we were talking about when a football players hit each other, there's that change of momentum. But one thing that we also need to consider is this term impact. The change of momentum, whenever that momentum gets transferred, however much of momentum gets transferred to one object to another, we call that impact. So the more change of momentum, the greater the impact. Does that make sense? So it's like, let's say you had a shopping cart. Let's go back to that shopping cart example. When you hit another shopping cart, if you just gently push a shopping cart and it hits another one, you're going to see a small impact. But if you are running with your cart full force and you just ram into somebody else's shopping cart, it's going to be a bigger impact, right? Which makes sense. You've got more momentum in that one cart versus the other. It has a greater speed, the second cart does, than the first one. So you're going to have a bigger impact. Now, when you have a big impact, the equation for that is F equals the momentum over time. And if we were to plug in that P equals mv for momentum, we get mass times velocity over time. Are you with me so far? Okay. So if we have a bigger impact, we can change one of these variables to decrease the force. So the impact and force is kind of similar. We talk about impact as being that moment when we transfer that momentum, when we collide and we create that energy, that force, right? That moment. But the impact or that momentum over time, we can change the actual force that we feel. So that is one of the reasons why airbags were created in cars. So if we were to just watch this really quick video, we can see how, let's actually watch just a couple of seconds. It's nothing too crazy, but cool. And it's worth listening to because they have a little bit of information to it. Yes. Were you about to say something, Abby? Okay. All right. So we don't need to know so much about counterfeit airbags as I just wanted you guys to see the airbags deploy. So what happens if you've ever, hopefully neither of you guys have ever been in accidents before. And if you have, I'm very sorry. And I hope that you guys are okay. It was minimal damage. But if you've ever felt if you've ever been in a situation where you are landing or hitting your head on a surface versus a cushion, right? There's a really big difference on the impact, and that's because of the time. If you are hitting yourself on a window, it is very quick to get to that window. But if there's a pillow there first, that you hit your head on a pillow, you're actually increasing the time, which then decreases the force that you feel in your head. And so that momentum gets decreased over time or is spread over time. So if we increase time, we decrease the impact or the force. Does that make sense? So in an effort, as a way to use momentum and manipulate the impact that an object has. So if an object has higher momentum, the change of momentum is going to be higher to that next object. It's going to have a bigger impact, meaning that's going to have more force. So the lab that we're going to be working on in lessons 1.5, 6, and 7 are really thinking about how we can use materials to increase the time that the momentum changes, right? So the more time momentum changes, the less of an impact it's going to have. So you are going to be creating an egg drop. You're going to be creating a helmet for an egg. Now, the interesting thing about this lab is it is to be designed. Now, there is no requirement for you to actually build it. But that being said, it's really fun. So if you have recycled objects in your house, like a box or wrapping paper, or thinking about egg cartons, right? There are all these things that we can use in our house that would help design it. So I encourage you to do it just because it's fun. But if you don't have the materials, no big deal. You're just going to draw a design that you believe is going to protect the egg from a one-story drop. So some things to consider. Think about the ways that eggs are packaged when you get them from the grocery store, right? Their egg cartons are designed in a specific way with a specific material to keep the eggs from breaking. In your design, you're going to want to include what materials you would use and how that material is going to help keep the egg from breaking. You are going to record all your models, so either drawing it, creating a 3D image, if you can do CAD, all of that stuff, and then post it in the discussion forum. So that is the overall thing you're doing for the lab. Couple of constraints for when you're designing it. You really can't have it bigger than a bowling ball. You do not want your contraption to be bigger than a bowling ball. it needs to, the contraption that you make needs to stay this. You can't see my lesson, can you? You guys are so funny.
We're on the screen where you were drawing.
Yeah, I realized that. I'm like pointing to everything, using my cursor. You guys are just so good and patiently waiting and listening.
I'm just
Okay.
listening to you.
Yeah. So here's the picture of the egg drop. Somebody, one person used a bunch of straws. And so this is what I was saying. So it can't be bigger than a bowling ball. It must stay the same the whole time. The same size the whole time. No parachutes, should be used from recycled materials and no hazardous materials. So nothing with chemicals, nothing like that, nothing that explodes. Once you create your drawings and your design, you're then going to go to your discussion post and you're going to look over your drawing, identify the materials used and the overall design, and you're going to list them in your post. Then you're going to go and read at least 2 other of your peers' posts. You're going to comment on their posts. And then you're going to go back to your original post and look at the feedback that you got from your peers. And then 1.7 is really just saying, finish, here's more time. Finish up lab 1 or 1.5 and 1.6. Okay, so that's the lesson. So I have a website that I thought was pretty cool, and it's totally up to you whether or not you guys want to work on it. I'm coming up to about, it is noon, so the lesson is technically over. However, that being said, I want to give you guys this website. And it's cool because it gives you like a little intro as to what you could do. It lets you play around with a couple of materials. Why isn't it working though? It's unresponsive. Well, if you click on it, it's going to take you right to this simulation where you get to choose in different containers and objects, and then you get to test it just to get you guys some ideas as to what materials you could be using in your house. Does that make sense? So I don't know why it's not working.
It's not working for me either. It's like a black screen. Nothing's popping up. Maybe it's like the link. I don't know.
Maybe it is. Let me see if I can re-find it. I am sad. This was a good one too. Here. Maybe you need to do this, except it's such a pain to get through. That's the only problem. Let's see. Okay, try this one. Oh, now it showed up. There we go. Does it work for you now? It should look like this. Oh, does it look like this, Abby?
Sorry, I was trying to refresh. I was trying to refresh the page, but I refreshed this one, so went out.
No problem.
Let me try refreshing this one.
Yeah, I mean, mine said that page was unresponsive, so I just clicked on wait, and then it showed up.
Yeah,
so if you
it's
click
still a black screen for me.
Okay, give it a couple of minutes, and then let me just show you what it's going to look like. So it kind of gives you the rules, kind of gives you a couple of things, and then when you click through all of the instructions, it's then going to give you your egg, and you're going to have a couple of options. So you can do cotton. You can choose to do cotton. Wrap your egg in cotton first. You can then choose to do toilet paper. Let's say you decide to do tin, and finally you put it in a lunchbox, and then you can test it and click drop, and then you can just kind of play around with a different bunch of materials and see with the simulation what would happen. So then you can go ahead and try it. It'll try different levels for you, but ultimately, so that one wasn't the best type of wrapping job, right? But your goal is to try to wrap it with materials that would allow you to make it to the top height. And this is just a way to get you thinking about products that you may have in your house or something that would be similar. And it's just something fun to do before you actually design it. Okay? But that's everything I have